The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everyone. This is Jennifer Beliveau with Triad Raised Access Floor Company. Thank you for joining us for today's presentation of predicting the performance of perforated floor tiles using high-fidelity CFD, computational fluid dynamics. I'm joined today by Paul Venus, the President and CEO of Applied Math Modeling Incorporated, featuring CoolSim, CFD modeling software, and Gary Meyer, the President of the Triad Raised Access Floor Company. Please take note of the questions panel on the right-hand side of your screen. We'll be taking questions at the end of today's presentation. If you have a question for us, please type your question in the question panel. Please also email us if you'd like a copy of a PDH certificate. Our email addresses will be shown on the last slide of the presentation, so you can email us then. Without further ado, let's get started. Paul?
Hi Jen, how are you? And Gary, welcome to the program today. I'm glad you're both able to be with us. Now, today what we're going to do in terms of an outline is just review some of the work that we've been doing on perforated tiles. This is a very high fidelity work that we've been working on together with Triad, and it has certainly opened my eyes to how important the choice of tiles can be, perforated tiles can be. So for those who weren't able to join last time, we're going to quickly review how we got the geometry in and what we did there and how we calibrated the model. And then we're going to take a look at the results of 3 different variations as compared to the Triad tile. So we're going to look at the 25% open standard tile. We're going to look at a 56%er, which is what I see used a lot for high density. And then there's a new tile as well we're going to take a look at that has become popular, and we're going to compare them against the Triad tile. And then finally what we're going to do today too is take a look at the economics arguments for change. And this has to do with return on investment. At what point does it pay back to go in and change what I have? So there's 2 points of view. One is it's a new build and I want to put tiles in. Which ones do I choose? The other perspective is I already have the data center. It's got tiles in it. What's the payback for switching out the tiles? A little bit of background. We're having trouble with density, all of us know, and that tends to be very localized. The density is high. It's in usually a 1U or 2U space sometimes in the rack itself. And traditionally what has, the solution to that has been just go with deeper plenums and more cooling capacity. But we already know that we have more cooling capacity than we need generally. That's not what I find the problem to be when I analyze data centers. But generally what we find is we have enough cooling capacity, but we don't have the air going to the right place. It's more of an air management issue really than it is a cooling capacity issue. So improving the air delivery system is key. And one of the fundamental ways to do that for raised floor data centers is to change the perforated tile. Take a look at what you can do in the tile area because relatively speaking it's low cost compared to the cost of a cooling unit or compared to the cost of adding extra capacity of one kind or another. Putting tiles in the floor, particularly for raised floor data centers, that's what we're talking about here, is a lot cheaper than anything else. But up until recently, the evidence has been hard to come by. It's been anecdotal at best. And so it's been empirical. The performance improvement has been empirical. So in early 2015, early last year, I gave Gary a call because I knew him. We had talked to him in the past years. And I said to him, you know, we'd like to take a close look at the Triad tile. And I made a bit of a bet with him. I bet him that we could do it because there was a question, you know, his question is, can you resolve it well enough to be able to produce any kind of meaningful output? And he had some issues prior with CFD in terms of being able to resolve the detail of the tile sufficiently enough to convince him that it was accurately representing physical phenomena. And I said, yeah, what we can do, I bet we can do it, and if I'm wrong, then you don't have to pay us. So it's kind of a bet. So we did. I think, Gary, it matched your expectations fairly well, and I think since then we've been moving forward as kind of a team, I would say. What do you think?
Yeah, that's true. Since I paid the bill, I must have been impressed with the results.
That's right. I won the bet.
Yeah.
So today, what we're going to look at, we did the first one. We modeled the triad tile itself, the ice tile, and then we took a look at, because we were able to do it, and he was convinced that we had the resolution to do it. We took a look at the 25%, the 56%, and today we're also going to review something referred to as 67%, which I'll let Gary define these a little bit more because he has a lot more experience with tiles than I do. So but what we're going to do is compare those three against the triad tile. Now, Gary, you gave me some photographs here for this webinar, and these are various tiles that you see a lot. Let's start here in the upper left-hand corner. This is a pretty standard 25% design that people would recognize.
Right. That, it's been out there for probably 50 plus years. And so that's what we see a lot in legacy data centers.
And in the middle here, I see this classical sort of 56%, right?
That's right. Right.
Yeah.
That one and the one to the right are pretty, both aluminum style panels, the upper right.
Yeah.
And so they both fall in that 50 to 56% range.
And then we have down here in the lower left, this is a fairly new design. Is that true?
That's correct. It's actually very similar to what you would see in clean room chase areas where the air is flowing straight down. And it's very wide open areas. It allows a lot of air movement, but it's more of a very high flow jet stream approach.
So the conventional wisdom, as I mentioned, is to keep the floors deep. Now, the reason that this is a popular idea is because there's two components of airflow. There's a dynamic and static pressure. The dynamic pressure is caused by movement of the air. It's momentum related. And typically in raised floor data centers, you have a fairly high component of dynamic pressure because the air is being shot to the center from perimeter downflow cooling units. That's often what I find in data center design. However, air is very lazy and doesn't like to turn a corner to come up out of the floor. So to reduce the velocity, a conventional wisdom is to make the floor deeper. If you make the floor deeper, the dynamic pressure declines, the static pressure becomes the dominant component, and the air comes up out of the floor instead of going past the tile underneath the floor. And then drive the prime pressure up to get the high flow rates, and then do a large open area to provide large flow rates through the tiles. This has been a conventional approach for high-density data centers. But this is expensive because you run into capital costs with the deep plenum. You run into the issue that in order to keep that entire volume pressurized, you need a lot of fan energy. And with the high percent area open, you need a lot of airflow, which is more fan energy. And oftentimes, it's too much. What you really want is you want your cooling airflow equal to your rack demand. That's what we call an RTI of 100%. For those of you who have been to DCEP training, it is when the rack demand, which, by the way, is roughly 156 CFM per kilowatt. So one quick way to find out how close you are is simply take the load of your data center, how much your entire data center is pulling, multiply it by 156, and then see if your cooling units are delivering that. Now, in a static case where they're single speed, that's easy to do. Just look up the flow rates of each of the cracks and sum them. If they're variable speed, there's usually an indicator somewhere that tells you how much of total it's running, and you can still add them up. The point is they should be equivalent. In an optimally designed data center, you only want to deliver the amount of air that is required by the heat load. If you supply more than that, what happens is it goes by the rack, doesn't get heated up, ends up in the return side, and is too cool for the heat exchanger to really be efficient. So it reduces the efficiency of the heat rejection system, the chiller, and it costs you money because you're pumping more air than you need to. But in order to get these things equal, it's all a question of efficient management of that incoming air. Now, Gary, you had done some testing here, and I'm going to turn these videos on here and let them run. And if you could just describe here what we're seeing, that'd be great. And I'll play this a couple times on the left.
On the left there is some of our early analysis when we first started being asked to analyze what's happening with the airflow. Since we have more cold air than we need, we started looking at what's happening as the air flows out of the airflow panels. The one on the left is one of the triad ice panel, and the one on the right of that first video with the streamers is a standard 25% perforated design that's pretty common. And we could start to see that there was some dramatic differences on just the flow of the air out of the top surface of the airflow panel, even though everything else remained the same, the supply, the flow, the static pressure, all that was equal. There was a radical difference in how the air is dispersing, how it's stratifying coming out of the panels.
So this is a test rig
on
that
the
you built.
right there,
Go ahead.
That's right. Yeah, this is a test rig we built that was Hitachi had actually designed it many years ago, and it gave us a consistent method of testing in a similar same setting, rather than variables of the way airflow panels been getting rated for years. There was just no consistency to it. Mm-hmm. So in that same test rig, then we broke it down. We took what we saw in the first testing with the streamers and some other testing after that, and we started raising questions. What's happening within the quadrant of the top surface of the panel in the 24-inch square? We broke those down into 4-inch squares to start to see, is there variation happening right within the panel itself? And what you're seeing here is, as this moves forward, the dramatic statement became, as the air was moving from left to right on this is a 12-foot chamber, 24 inches deep, and you can see there was actually a reverse draw on the panel on the right, a 56% panel. It went to negative 520 CFM, but it shows very high stream. If you'll rerun that again, Paul, at the very top corner, it's actually flowing a lot of air, a very high CFM. And so what we started to see here, and this again, the triad ice compared to this 56%, it went from very high, it drops down to 332 CFM. It's fairly consistent in the center of the triad, and that was part of the design we were after. Just moving it over 4 inches, which is right there, you see a 500 CFM jump, which means we've got a wave effect going on. Mm-hmm. And then the final move, when we looked at to the front of the panel, that's where you see this negative. And some of the testing analysis that Paul's group did actually validated what we were seeing live.
Mm-hmm. So I thought it was interesting that you already had test data. Of course, this allowed us to validate the model. Now, here's another view here. If you want to just annotate this a little bit. Over here on the left, we've got, I think you call this the popcorn test, right?
Right, yeah. We went from the streamers we tried smoke that dissipates too rapidly to really see what's happening with the turbulence or the flow. And that's what we were looking at, is if we had plenty of cold air, why aren't we getting better cooling efficiency through the server rack? And what you can see with the popcorn, you can actually see that front draw down. It's a short cycle effect,
right? Even
though you're getting flow at the back end of it.
So this effect on the leading edge is something we'll...
You're seeing the same stratification.
Yep. And over here is the 56%er, right?
Right. This is the 56 that we were looking at with the handheld venometer testing. And again, it gets better stratification. It actually gets up to about 5 feet. but if you watch it as it moves, there's an acceleration back down to the front of the panel, which is that short cycle we were seeing with the handheld venometer where it showed a negative 521 CFM. So we could physically see the flow of the air by using this popcorn analysis.
Now, the experimental apparatus that you were using looked a little like this for the viewers that just saw that. There was air moving under the floor, managed pressure using a flapper valve on the backside, so air does pass underneath these tiles. And it's a test apparatus with a supplied airflow generator on one side and a damper on the other side. That's really what it looks like. And then the tile, this is a top view, single tile at a time. Now, as Gary mentioned, broke it up into 36 quadrants and made measurements on each one of those quadrants using about half an inch of water, or 0.05 inches of water. And this is what your data looked like, right, Gary?
That's correct.
Mm-hmm. So our first task was to take his tile and build a virtual CFD model of the same thing and see if we could match that kind of performance. How close could we come to the data? Now, interestingly enough, we hadn't seen this plot that I showed you in this earlier slide. We hadn't seen this yet. I asked for this later. So it was kind of a blind thing. We had seen the videos, and he had showed us those. But we took the tile itself and we brought the geometry into Fluent, actually, the Ansys Fluent tool. We actually used their ISIM CFD tool. We are an Ansys partner, and I kind of grew up at Ansys, so we used those tools to mesh this, and you can see the mesh is very fine. We used a body-fitted mesh here. This is a tetrahedra body-fitted mesh, so we were able to get right up on these fins. You notice he's got an underfloor fin design. We're looking at the bottom of the tile, and we're looking at these fins, and they have a unique shape. They're curved in two directions. They arc this way, and they also arc this way. So it's a two-directional kind of curve he's got on those fins. Very interesting design. The mesh count for this one tile alone was 9.34 million cells. That's a fairly large mesh, particularly for a tetrahedra body-fitted mesh. 9.34. It's not huge. I mean, in Fluent, we get them. You know, we've seen them in other applications run upwards of hundreds of millions of cells, but still, for one tile, that's quite a mesh. Now, in terms of simulation, we ran it as a steady-state isothermal solution. We consider just one tile. We used Navier-Stokes, of course. It was the Fluent solver, K-epsilon turbulence model, first-order discretization, and we drove all the residuals well below 1 to the -3. This was our test rig. This is the one we built. It's a virtual model, of course. It's done on the computer. But it's the same kind of test rig that Gary had. And we let the room be open to the atmosphere. We ran it a little harder than he ran it. We ran it at about 0.05 to 0.056 inches of water. It was a little higher than he ran his at, 5,100 CFM coming in. We used air with a density of 1.225 kilograms per cubic meter. That's sea level with a standard viscosity for air. So that's how we ran. And so I called Gary up after we had done the run, and I said, do you have any data? And that's when he handed me the experimental results he had made with his handheld device, and then we put the CFD results on top to see how we'd come out. And I think, Gary, it's fair to say at this point you were convinced, right?
That's correct.
It's a bit of an understatement, Jen. He got pretty excited on the phone when I first showed him. They said, "Oh my God, I can't, you know, I got to show this to my wife. Look at that, my God." I don't know if she was impressed, but. And we started to do.
I hear you.
We started to do some work on it to look at the flow as well. And one of the things we noticed once we had validated the data is the tile was putting out flow from nearly every spot on the tile. This is at 0.5 feet. What we're doing here is looking straight down at the tile, and we've taken a slice at half a foot off the floor, and we're looking here at velocity as a function of color. So you see that it runs all the way up to 230, and there's very, very little of that tile that's not putting out positive velocity. So it looks good. I mean, you want that kind of image, and you'll notice as we roll through some of the others that it doesn't look quite that good. And the next thing we started to do is we looked at a cross-section. We sliced in this direction. So here we're looking straight down at the tile. This is a bird's eye view looking down at the floor of our simulated model. And we're taking a cut right straight through it, and we're going to show you that over here. So this shot is sliced halfway through the tile, and we put some simulated racks in place here. So there's an outline of a rack you can see right here, and an outline of a rack here. And we're looking at flow, and in this case we're looking at velocity as, again, a function of color. So at the top end it's running at 900 feet per minute. Down low it's of course 0. So we take color and spread it across the whole range, and you see that the air is coming up and covering that whole rack pretty nicely. And furthermore, it's angled a little bit. This plot right here is an ISO plot of velocities greater than 180 feet per minute. So we said, okay, let's look at the data and let's filter out all velocities greater than 180 feet and see what that looks like. And again, you see this nice plume here, much like you see the one on the left. So at 7 feet, these were operating at 271 feet per minute of velocity. So it has good momentum all the way through the entire height of the rack. So it looked pretty good here, and it looked very much like what Gary was seeing. There was also an angle to the flow of about 18 degrees. You can look at it from just a flow point of view or from a velocity vector point of view, but we got about an 18-degree angle of incidence towards the rack. So it's redirecting the flow towards the rack, and the flow here is from left to right in our tests and in his test fixture. Flow starts over here on the left, coming across under the floor out the other side. So the effect of the fin there is to catch that air and redirect it back towards it. It actually does a bit of a bounce off it and redirects it back towards the cabinet. Now, this assumes air only comes in one direction, to the left. That's the only place we measured it, was left to right. And in truth, what happens under a floor, and Gary, I'll bring you into kind of, you've had more experience sort of with this tile than I have, but as it turns out, velocity comes from all directions under a floor typically. So this kind of effect isn't just precluded to coming in one direction. It actually spreads out everywhere, I would think, in real life, right?
That's right. Yeah, because you have eddies underneath that floor just being stirred up just simply from the pedestal understructure themselves or the stringers, which is actually, it affects that movement of air. And so the design of the anterior fin was designed to work like an airplane wing. So there's lift and drag on both sides no matter what direction the air is coming from.
Right.
To give it a direction. That's the intent of it.
Now we also took a look at the front of the rack, and we said this is an imaginary rack, it's just a block, but we're looking at velocity as a function of color in the height direction. And you see here that the velocity you see, it's bouncing, it's going into the rack and hitting the rack right about the bottom third. It starts and bangs right into it pretty hard. So this is velocity, horizontal velocity into the rack right behind the tile. And that of course looks pretty good too. So then we started to say, okay, well, let's take a look at how it compares. So in the comparison, we first took a look at the 25% tile in an open environment and compared it to the triad tile. We wanted to compare velocities and flow paths, just like we just did. Same idea. We wanted to do some comparison, look at the stratification. So the first one we took was a 25% area open tile. Now this one you could recognize. This is a very standard tile. It takes a lot of cells to capture that geometry. We brought this in straight from CAD. And you can see here these holes are very small. So this is, again, 11 million cells for one tile. And this one, Gary, I see a lot of these are flat bottomed. They've got some sort of pancake thing on the bottom of them as well. We didn't have that in this case. But can you comment about the understructure of this and how it often looks?
Yeah, I was breaking up a little bit there. What happens with the flat bottom is the air flows across, and that's what's causing some of that short cycling you're seeing. But the structure, either they have this kind of egg crate look, or some of them actually have a dimpled cupcake look to the bottom of them.
Right.
And what that does is it creates a turbulence right there.
Yeah.
And what we're trying to do is get a laminar flow at the bottom of the tile, directing it upward to change it to a turbulent flow within the cold aisle itself.
So my point here, Gary, is that we're probably giving this tile the benefit of the doubt here by not putting that pancake thing underneath it, because I notice there is in some cases when I lift them up this sort of what you call the pancake or waffle kind of structure underneath it that is going to make the situation worse. So here's what we found. We found the ice panel had better flow rate, about twice the total flow coming out as compared to the 25%er. And furthermore, if you take a look at it, you get an awful lot of dispersion on that 25%. If you look at the 7-foot level for both panels, you got 271 on the triad tile and only 147 on the 25%er. So it doesn't hold its momentum very well, and you can see that all the way across the tile. If you take a look at different heights, if you step from half a foot up through 7 feet, you'll see that the ice panel is maintaining its momentum, and the 25%er simply does not. In fact, what happens here is it actually, if we take again a look at this iso surface, again this is all data greater than 180 feet per minute is shown in red, and you show on the left, this is the plot we showed before where you've got good momentum all the way up through. Over here on the right, there seems to be this sort of puddling going on where it comes out and just sort of stalls. It doesn't really go anywhere. It's fairly good at the bottom half of the rack, but you're not getting any cooling near the top of the rack. And this is pretty much what we saw in the videos as well. At about 3 feet, at 25%er just dies. And here's again, this is a 3D ISO representation of all flows greater than 180 feet per minute, same as I showed before. We're just showing it to you in a 3D ISO representation, and you can see it's overlapping the rack right there and causing good cooling, good penetration. This will cause turbulence on the front end of that rack, and it will cause cooling to occur because you're directly infiltrating that rack with cool air. Over here, not so much. I mean, you've got to hope that this air right here is cold enough to cause the heat to transfer through the air by itself without the help of any convective force, and that's tough to get done. So, and this reflected pretty well the test, I think, Gary. I mean, here's over here on the left, I've got your triad tile next to the standard tile that we showed earlier, and over here is the simulation results on the right, which mirror that almost perfectly.
Right. It's almost exactly what we were seeing.
Now, if we look at the front of the rack as well, we see a similar pattern where the air here is striking it and getting good penetration on this rack for almost the whole length of the rack. Over here on the right, not so much. You're just not seeing it come in with any great speed at all. And the angle is not as good either. If you take a look at the angle of incidence, it's not nearly as strong. So triad tile looking much better. We also took a look at the 56%er. This one was very interesting. This is a design I see a lot when people are using high density. They put these in. And the flow rate coming out of this thing is incredible. 1100 CFM coming out of that tile, almost 20% of the total flow, a little over 20% of the total flow going underneath it comes out there. And here's what you were referring to. This is a jet. If you take a look at this, it's just ripping straight up into the air. If you look at the velocity at a midplane, 456 feet per minute. In other words, high velocity is not perfect. It's not always good. You need enough velocity, but here under the same conditions, by the way, our fan's having to run harder and we're dumping more air. So this is under high energy consumption situations, you're getting this big jet. And what's happening under the floor right here, this is the same exact geometry that we brought in mesh, and you see now under flow conditions, again, flow moving from left to right. What it does is it hits this leading edge right here, and the flow separates. It's a separation right here, and it goes way out and doesn't come back until in this area here. So here's exactly, Gary, some of the readings you were seeing. So there's your, with your velometer, there's your low pressure reading right there that you showed us. There's your high velocity region right there. And here's your reverse right here. This one is going to create a situation where you've got recirculation on that leading edge because of this piece of geometry. So this tile is not a good tile for cooling a data center. It's got two problems with it as far as I can see, Gary. One, it's that the jet is very small and concentrated and very, very high velocity. And number two, the cold air is going up to the ceiling. So if you've got a ceiling plenum return or even a conventional convective return on your crack unit, it's going to put cold air back into that thing. It doesn't send it through the rack. So not a good comparison to the triad tile. So, and it has no angle at all. The angle's, you know, less than 5 degrees or 5 degrees or less. And then if you look at the same plot of how much air is going into the rack, it comes up zero. There's no air going into the rack here. In fact, I would argue, Gary, that there's so much air going by that rack, it probably produces a low pressure and it makes the fans work harder. Have you ever witnessed that?
Yeah, it's actually, we're part of National Science Foundation studies as well, and they call it entrainment, that the air is moving so fast that it's actually enslaving the server fans trying to pull air in, that they're having to run at full bore, attempt to pull anything in it, and what's happening is pulling heat back through the face of the server.
Yeah. It's
just moving too fast.
Yep, yep. So if you look at the comparison to the ice tile, you're dumping more air into the room. 1102 versus 763, that's almost 50% more compared to the ice tile. Yet it doesn't cool nearly as well. If you take a look here, this is a side-by-side again. This is the 56%er on the left shooting a jet right towards the ceiling. We're over here on the right. Not as much air being dumped, and the air that's being dumped is being directed to the rack, and it's diffused. It's beginning to spread out as it goes up, forcing itself right into that cabinet. Here's a side-by-side that I thought was worth showing. Here on the left, you've got that, again, the 56%er, a big area of separation right underneath the leading edge. Over here on the ice tile, because of those fins underneath, it's picking up the air. It's grabbing it and pushing it up. So not a terribly complicated thing to understand. It's just redirecting is what it's doing, the air underneath the floor. And again, it's assuming these are all exposed to the underfloor, and in cases I have seen that isn't always the case, that those are exposed either due to a pancake design underneath there or something else. Flat bottom tiles don't work that well, I guess.
No, I mean, directional vanes are not new to the HVAC industry, and basically that's what that anterior fin is saying. It's going to direct the air rather than just passively hope it comes up through the bottom.
Again, another plot of isosurface of velocities greater than 180 feet per minute. Angle of the airflow is only 5 degrees at best compared to 18 for the ice panel. And again, we showed you compared to the ice panel, there's no air going into the rack compared to the ice, which is delivering a good air into the rack all the way up. This was also an interesting plot. We're looking at area of recirculation here. So these are negative numbers. So what you see here on the left is, again, the 56%er. And we're showing velocity in feet per minute, both positive and negative. So we wanted to show off the recirculation here. Look at it. It's that leading edge, and this is exactly where you put your velometer when it went negative. And that's what we're seeing. Almost 20% of that tile is running negative, where on your tile it was hard to pick up any at all. Probably if you put your velometer way over here on this leading edge, you would have measured a little. But there's very little area where it's negative, about 3% in terms of the total area. Now this is a new one.
Part of that is good.
Go ahead.
Part of that is because no matter what way the air is coming from, you have a leading edge, a stringer of some sort in that understructure. And so you have a natural bridge or bank there that the air is going to hit. Mm-hmm. And that creates that downward motion.
Yep. It's fairly easy to understand once you've done the analysis. It's clear. Now this is a fairly new design that we see, or you have seen, that's in the market. This is a design where there's fins on top. So this is, I think here, Gary, what it looks like is a 56%er with fins on top. Is that a fair characterization?
Well, they actually call it high. It's in the 60 to 67% range, they call it. It's basically a grate system that we saw in the clean room industry. Chase, it's a non-occupied space. But the attempt was here is to put the bend at the top of the panel in order to theoretically direct the air into the server. But again, it's moving too fast.
Yeah, now if you look at this straight on, without knowing what we've learned, you would say, well, that's pretty good, right? Air's coming straight up through the floor, and then these would bend it one way, and then these on this side would bend it the other way. The flaw in that analysis of that conclusion is that the air is coming straight up out of the floor. It doesn't. The air moves horizontal under a floor, at least many floors, unless they're very, very, very deep. Again, I get back to this issue of dynamic pressure versus static pressure. If there's any movement of air under that floor, and of course there is movement because it has to come from the cooling unit out of the floor, so it has to travel across the underfloor. If that velocity component moves up at all, for example, you've got a shallow underfloor. I see many underfloors 18 inches, even 24 inches. I've seen them 12 inches. I've seen them, Gary, as low as 6-inch floors, and people trying to use them for raised floors. So you have any of that horizontal component, this thing breaks down and doesn't behave itself correctly. So here again is the flow rate, the 1200 on this one versus 700. So this one's even worse than the 56er. It's 1.6 times. And look at the flow on this one compared to again, over here on the right is the standard ice tile that we've been analyzing and looking at. But look at this one. The jet's even worse on this one, Gary, and it's got more separation. If we zoom in and take a look at this one, this one looks, whoo, I don't know, that doesn't look good to me. What do you think?
Well, I'm not spending my money on it.
So what you've got is a couple problems here. One, this leading edge again is causing all kinds of problems. So these fins that are here never get to see the air. There's nothing there for them to do. The air is not moving up. It's coming across like this, and then finally it starts to slow down, and it bangs into this guy, and so you get very high velocity right there, and then it moves up. But then you get a gap, a separation on the back edge of this one. And so you get a hole. And then over here, it comes back in, slows down, it comes back in and hits these, and then it directs. I mean, look at the velocity you've got on that back edge. It's just crazy. So the flow ends up being separated and sort of all joined together or compressed over here on this side. And again, same exact conditions. All we've done here is change the geometry, and the ice tile is performing much better. So look at the separation on this one. We've got a gap in the middle of it where no air comes out at all. And then over on this side, we've got very, very high velocity. And then on this side, it's busted up, and the velocities aren't nearly that good. So it's kind of an interesting design. This one does throw a little bit better air at the rack than the straight 56%er, but it's not nearly as uniform. You see, it sort of collects in one spot, and it's not nearly as uniform as the triad tile. And furthermore, you're losing all your plenum pressure, and you're having to drive it with a very heavy fan, and it's got terrible recirculation on the leading edge. Almost a third of it, Gary, is recirculating on the leading edge of that tile. So again, this is top-down view, flow left to right, and we're looking down at it, and we're plotting negative velocity. This in blue, it is, if you were to put a piece of paper on this leading edge of this, it would suck it right to the floor. So instead of air coming out, you've got air going back in, which can't be good. I can't imagine that's not what you want.
Right.
So it looks like the design I don't know how you came up with it, Gary. I really don't, but whatever you've done here, it's working. It works better than anything we've looked at. It's better than the 25 and 56. And there seems to be here a good opportunity to use fewer tiles with shallow plenums. Not a lot of people, I mean, I run into a lot of data centers that are 18 inches. I mean, that's not uncommon. If we're lucky, Gary, we find them at 24, right?
Mm-hmm. Right.
So you don't need to.
Part of,
Go ahead.
yeah, a big part of this is the science of heat transference, and that you asked where I came. The design was to start from the face of the servers, and what's restricting. We got plenty of cold air. We've all known that for a long time. So where's the breakdown? And the breakdown is in the design of the airflow panel itself,
mm-hmm.
and what the geometry needed to change in order to make it effective.
Yep. So you can run the triad with lower plenum pressure, lower fan power, increased air temp. It's going to help the chiller. So we did a quick study here on a 20,000 square foot data center. This was a 30-inch floor. A total number of racks here 807. 807 tiles. And the costs here are right around $105,000 for the tiles, assuming they are about $130 a piece, which that was math you had, not me, but that's a pretty fair number, you think, there for the tiles, Gary?
Right. It's pretty close to suggested sell price.
Total airflow here is about 500,000 CFM, 455. Static pressure 052, air supply temp 50 degrees, 55 degrees F. Now the annual cost based on that for fan power, chiller, they're assuming an average COP of about 3.5. Fans, assuming horsepower for the fans to generate that amount of CFM is calculated there, and therefore your total cost to operate for chiller, fan, and IT is about $3.5 million to run. Now, what you can do with, and Gary, you can weigh in on this anytime, but we worked on this together. You said, no, you don't really need a tile for every rack. You can stagger them. So you see over here on the right, you were able to operate in a configuration which is every other for that density, 3 kW, by the way. This would drop the total number of tiles down, and therefore, but your price is a little bit higher for your tile, but so the cost is $141. If we just step back, the cost was $105. But you can run the cracks at a lower flow rate because you don't need all that flow anymore. Static pressure 0.04, drop that down and move the air temp up a little bit. 65 degrees, we moved it up 10 degrees. 10 degrees will get about 20% efficiency improvement in the chiller, which is reflected here in the lower chiller cost. Fan power is lower because you need less pressure, and it drops it down from 3.5 million to 3.178, savings about $350K per year. So this is a fairly good representation of what you've seen. Do you want to provide any commentary on that, Gary?
Sure. Basically one of the triad ice panels will do what 3 standard panels will do, or 2 of the 56 to 67% panels, simply because of the change of directing the air, making the panel positive all throughout, and then going into heat transfer science at the face of the servers. So it's not about this, you want air that's presented to the servers, the server fans can use more readily and not be enslaved. And you don't need as cold air because now you're using fluid dynamics, managed fluid dynamics, to transfer heat. So a big part of the triad design is what happens inside that cold aisle, not using laminar jet stream flow versus turbulent flow, which transfers heat 4 times more effectively than laminar flow will.
Mm-hmm.
So that's why you see the effects.
Now, I should make a correction here. This shouldn't say 25%. In the earlier slide, it's 807 25%ers. This one, it's 410 of the triad tiles, not 25%ers. So just a typo there I noticed that I made. But significant savings, Gary. I mean, payback on that is just really less than a year, I think, to do that compared to, yeah, I mean, if you put them all in, if you replaced all those tiles, you'd pay for it the first 6 months of operation, according to that set of numbers. That's pretty quick.
Yeah, we have a lot of end users that, yeah, we get repeat end users saying 3 to 6 months because of the power utilization savings on the cooling.
Yeah.
So 1 year is very conservative.
So save both CapEx and OpEx. Don't have to run as deep. Less material to support the floor. Doesn't have to be quite as strong because it's not as deep. Containment might be able to, and this isn't an argument necessarily against containment, but containment's not inexpensive, so you might be able to put it off for a while, or in some cases do without it. Lowers the total tile cost in inventory. You don't need as many, and reduce the fan speed. That's a big deal. Remember, fan law is cubic, so every time you move it down a few RPMs, you're getting a cubic relationship and power savings associated with that fan. So that's why VFDs are very popular. So this will work very nice with a VFD system. And you can increase your air supply temp, which is going to make the chiller more efficient. Ratio there is about 3.5% for every 1.8 degree F that you raise the supply air temperature. That's a rule of thumb that's pretty popular in the ASHRAE community. Again, 3.5% average energy savings for every 1.8 F you move up. So if you move up 10 degrees F, you're going to save about 20% in chiller efficiency. In general, that does not assume any kind of economizer is being used. If there's an economizer in that loop, it'll go up much higher than that. So it's a conservative number. And of course, your maintenance costs drop. So just kind of summarizing here, we're about 45 minutes into it. I want to leave enough time, Jen, at the end for questions. Type of tile makes a big difference, according to what we have found through studies, through analytical studies. And this idea of going for deeper floors may not be required if you choose the right tile. I am shocked how poor the generic 25%er is at cooling upper sections of racks at all. And then the alternative, 56%, is like punching a hole in your balloon. It just all comes out in a jet right towards the ceiling, cools off your return air temp, which is bad for the chiller, and also doesn't provide good cooling because of the pressure problem in the front of that rack. The newer tiles that have been introduced aren't that much better. So it seems like you've got something there, as far as I can tell, Gary. You got yourself a nice tile. So Jen, let me turn it back over to you. We can open it up for questions and take any of them that you would like to direct.
Excellent. Thank you, Paul. Thank you for those of you that have submitted questions. The first one I have is, how should cabinet U positions closest to the leading edge be consumed and or managed?
Well, let me just back up here to the shot of that triad performance, because there's a couple things about it. Let's look at it right here in this shot. Now, the good thing here, Gary, about being down low, these are the U's down low on the rack. Now, the thing about a raised floor data center with cold air is the high density air always sits at the bottom. So although you don't have velocity pushing into the rack like you do, say, from about a third of the way up, what you have at the bottom is a bunch of cold air. So I would think in this kind of configuration, it's fairly insensitive to location. What's your experience?
It hasn't affected the way that, because of that anterior fin, the rocking chair's designed to it collects less air at the outside edges. So that actually slows down bringing the air up through the panel, the direction of the air. That is what will feed the lower part of the rack, because we don't want the air moving too fast at that point.
Right.
So we haven't, the proximity, it hasn't been in effect because, in fact, we use turbulent flow, and that will disperse into the face of the rack.
Mm-hmm. Okay. Jen?
All right. Next, the floor plan indicates a pretty wide lateral spread across several cabinets. Is there any flow analysis to support that? The ice tile seems to direct the flow at a single cabinet base.
I think they're talking about this pattern right here on the right. And you and I have talked about that a little bit, Gary. And again, I think the answer is that we did an analysis assuming that the air was coming from a single direction. And in fact, what happens is air under a floor is coming from every direction because there's a lot of turbulence under that floor. And so the effect we're showing you on one cabinet is actually spreading out onto the others as well as a result of that. Is that what you've seen in practice?
Right. What we see in live studies where they're doing thermal imaging is one panel, it actually fans out while it's directing it to the face of the cabinet. It fans out across the cabinets to the two sides of where the panel's located. So it actually does cool 3 racks, depending on the kW in each rack. But it's that is part of the turbulence that we design. It's really not, that part is very hard to show in CFD modeling. This was a big breakthrough for us just to get to this part. But it's still, you're taking kind of a slice shot versus the whole, you can't see the whole pattern dispersing.
Right.
I think that's correct, Paul.
Yep,
right.
yep. Okay. And by the way, what we always do, Jen, is we take CFD modeling and we sort of compare it to industry, to empirical evidence. So the empirical evidence largely comes from Gary, who's had experience doing this. What he always lacked before was the analytical piece to validate his empirical evidence. I think, Gary, is that fair? So yeah, you want to go ahead to another question, Jen?
Sure. All right. Would these triad panels work with a variety of floor tiles on the market, mostly with respect to the height of the surface of neighboring tiles?
I think that one goes to you, Gary.
Mm-hmm.
Yeah, that's actually part of the patented design, is it can be leveled, it can be adjusted to any floor system out there, and it can be leveled to varying heights. So a lot of raised floors either have 16th inch laminate or 8th inch laminate, or some of the old Don Liskey or very deep panels. So we're able to adjust the height of any panel, and we can adjust to the understructure design horizontally for a tight fit.
Okay.
All right. You ready for another one? Okay. Would you suggest rotating the tiles to maximize the airflow to the front of the rack, or do you always place them in the floor in the same direction?
I think that's over to you as well, Gary. What's your experience?
Yeah. Well, our experience has been is that you optimize the stratification, the height of the flow, by turning the anterior fin towards the main supply source. As we discussed, this air is moving in all 4 directions. So that will optimize your throw height, your stratification, which we try to maximize at 7 feet. We want to, if you notice, our CFM slows down. We want to slow down at 7 feet and kind of create a bubble, like a ceiling lid there. And so when you get too high of stratification, and that's all driven by static pressure. If you're getting static pressure 0.05 and above, you're going to see a throw above 7 feet. You're going to get up to 8 or 9 feet. By turning the anterior fin away from the supply, perpendicular or reverse, what it does is lower the stratification. It doesn't change the dispersion. It doesn't change how the turbulent air transfers heat. It changes the height of the throw. But if you point it towards the face of the main supply, you'll get, that would be the way to design it to standardize stratification height based on your static pressures.
Mm-hmm. Jen?
All right. And next, why is the jet flow traveling straight through the rack?
The jet flow, well, it doesn't go straight through the rack. I think they might be talking about, let me just back up to this shot right there. That's one of them. The other one is right there. And this jet, it doesn't go through the rack. Over here on the left, this is the 56%er, and it's going straight up into the ceiling. Now, what you want is you want some air to penetrate this boundary, this cabinet boundary, like over in this shot. This is the ice panel. What happens here is as that air comes up and bangs into that panel, it creates turbulence, and that turbulence causes the heat to transfer, the convective heat to transfer. So you want some intersection of the air, cool air coming out of the floor with this area. It doesn't really matter, to be honest, what direction the velocity is. If the velocity is banging into it at an angle, it's going to intersect that front edge and create the turbulence and swirling that occurs on that front edge, and that's going to provide the fans and the servers with nice cool air. So it doesn't actually jet through the rack, it just comes up and mixes. And you get this mixing that occurs between the cool air on the front of those racks.
Now on that, Paul, what we're seeing, there's kind of a terminology out there now about capture. One of the things that's a myth about that you mentioned is there's a boundary layer right at the face of the rack. It's created by two things, the heat and by the rack door itself, the screen mesh that we see there. Air and water do the same thing. They take the path of least resistance. And when it's running up to this boundary layer, the heat layer, which is kind of like a wall effect, or they're running up to a screen mesh that has small porous holes, the air net is going to want to go to the largest cavity. It's going to move. It will bounce away. And that's what we're seeing with these panels that are delivering is it's moving so fast, and that's what's causing some of this entrainment of the server fans themselves, forcing them to run at almost full speed. And some of the studies have been out there now. If the air is presented correctly, the variable speed fan in the server itself will reduce its energy usage by a third if the air is presented correctly.
Wow, that's significant.
All right, you ready for another one?
Sure.
Are the rocking chair fins directional? Are they more effective with a certain flow direction?
I think I talked about that.
Go ahead.
Yeah, the rocking chair anterior pin does create a directional flow, but because of our intentional design of our pattern to change laminar flow from underneath to turbulent flow above, it actually fans out. So it does create the direction I think they're talking about, but it also creates a turbulent flow which transfers the heat across the face of three servers.
All right. If you have two tiles consecutively placed in the floor along the laminar path of air under the floor, how would the airflow of the second tile be affected?
Well, it would have a similar behavior, I think, in that it would still grab some of the air going by and pull it up. I think it would behave pretty similarly to the one in front of it. The fins redirect, and so the redirection is going to take place no matter what because they're grabbing the air under the floor and redirecting it, I think. Is that what you've seen, Gary?
Right. That's exactly the purpose of the anterior fin. Is you need to tell air and water what direction you want to go rather than just passively hoping it'll come up, leak up through the airflow panels, which is basically what a flat bottom design has to do. The air has to find its way there.
Okay.
All right. And this one's also for Gary. What is the angle range for the slots in the tiles?
The angle range. but if you look at our ice tiles, we use varying size of orifices, hole openings intentionally, and so the angle is actually being driven by the anterior fin, and it creates a throw. I think that's what Paul showed in one of his slides. It was 18% or something like that.
Yes.
I think that answers the question.
Mm-hmm. Okay, Jen?
All right. In your simulation, show the 18 degrees from vertical. That angle can be predicted with underfloor turning gain. Are they omnidirectional underfloor in that instance?
I think there what he's trying to say, Gary, is are those turning vanes movable? I've seen this question come up before. Can you adjust them? And conversely, what about, of course, you and I have talked about this. We showed air coming at that tile from one direction. What if it comes from the other direction? We haven't modeled it yet. It is something we could do, if you want. But what is your experience with air coming at that tile from a different direction? Do you often rotate the tile for best effect, or does it have an effect, or what's your experience there?
Yeah, again, it comes back to what height they're trying to stratify. If you're trying to stratify at 6 feet, and that's driven, or 7 feet, or 8 feet, or even 9 feet, and that's driven by the static pressure. So you can turn. We actually have tests going on through National Science Foundation where the panels are rotated during testing, aside from what we've done here with applied math. And it does not show much change at all, perpendicular or straight on. When it's totally reversed from the rear, it does have it changes the stratification height by about 12 to 18 inches because there is a natural damper, but the anterior fins, again, have lift and drag no matter what way that air comes from.
So it's fairly insensitive to angle, although you sometimes rotate them, but I think what you've told me before is 90 degrees is usually all you have to do. And by the way, rotating them 90 isn't a difficult thing to do, right?
Right. They have handles built into them. It's pretty easy to turn.
Right. All right, Jen. Any others?
All right. We've got one last comment for you. Your CFD setup shows the primary airflow going from row to row, not along an aisle. However, most data centers are laid out with flow along aisles, not across them.
Yeah, I think this is the same. Question, Gary. I get this a lot. Can we see analysis of the flow moving along the aisle instead of perpendicular to the aisle? And the answer is yes. We just have to change the orientation and squirt the air in the other direction. It's easy enough for us to do. It may be something you want us to do in the future. It's up to you, but it sounds like we've got a couple users who want us to run more models or more variations to see how it performs under different conditions.
Yeah, I'd be glad to do that. We know from live experience that it performs, in 99% of the settings, no matter what direction the air is being supplied from.
Okay, it is coming up on the hour now, Jen. I try to keep these to an hour for our users. How are we doing on questions?
We are all set with questions.
Okay. So let me just get to the end here and thank everyone for coming. I want to put this last slide up so that we can have the email address. I want to thank everybody for coming today, and if there are any questions, there's our email addresses right there. Please go ahead and let us know. Jen, any closing words, or Gary?
I appreciate the time. I'm very pleased to have this scientifically validated. It's excellent.
Okay.
And thank you all for attending. We look forward to having you attend a future presentation. Have a good day.
All right. Thanks, everyone.